In this video, we'll look in more depth at two specific Azure Storage services, the Blob service and the Table service. If you would like background information on Azure Storage in general, please watch the precursor video, Azure Storage Overview. First, we'll talk about Blob storage. The Blob service provides storage for entities, such as binary files and text files. Every blob has a name, and it has a unique URL, as shown here. The REST API for the Blob service exposes two resources, containers and blobs. A container is just a set of blobs, and every blob must belong to a container. Unlike a traditional file system, there is not an arbitrary hierarchical nesting of containers within containers. However, blob names themselves can include the / character, so you can produce something that looks like a tree hierarchy using this naming trick. A storage account can contain an unlimited number of containers. Containers are useful because access policies and metadata are set at the container level. They are not set at the individual blob level. The metadata is limited to 8 kilobytes of arbitrary name-value pairs. There is a special $root container which serves as the default container for your storage account. The root container is also useful when serving Silverlight and Flash out of blob storage. You may need to store cross-domain access policy files in the root of the domain. The Windows Azure Storage infrastructure strives to maintain a constant 60 megabytes per second throughput for each blob. This criteria is what all the internal load balancing machinery targets. The Blob service defines two types of blobs: block blobs, which are optimized for streaming, and page blobs, which are optimized for random read-write operations. Page blobs provide the ability to write to a range of bytes in the middle of a blob. They're handled very differently in the Azure API, and they are handled internally very differently by Azure. Block blobs should be thought of as a sequence of blocks. There is a limit of 200 gigabytes for a block blob. They're intended for streaming workloads. Page blobs have a much larger size limit of 1 terabyte. They are intended for things like virtual machine hard drives. All blobs are read with a getBlob operation, which can specify what range of bytes to read. Writing content to a blob, however, is very different, depending on whether it's a page or block blob. To write content to a page blob, you call the putPage operation. The writes to page blobs happen in place and are immediately committed. Updating a block blob is more involved. Block blobs less than or equal to 64 megabytes in size can be uploaded by calling the putBlob operation. Block blobs larger than 64 megabytes must be uploaded as a set of blocks, each of which must be less than or equal to 4 megabytes. Then a call to putBlockList is called to commit these newly uploaded blocks into the blob itself. If you do not call this function, then the uncommitted blocks will eventually be discarded by the Azure system. One nice aspect of this is that you can upload many blocks in parallel out of order. The order of blocks in the call to putBlockList is what ultimately gets committed into the blob. This slide illustrates another aspect of page blobs. They are aligned on 512-byte boundaries. Each write to a page blob can overwrite up to 4 megabytes worth of pages. Writes to pages happen immediately, unlike with block blobs. Now let's look at the table service. The table service provides structured, schemaless storage in the form of tables. It has a REST API that is compliant with the ADO.NET Data Services REST API. Azure's table storage should not be thought of as a traditional relational database table. It does have functions like query, create, and delete, but there's no fixed schema and there are no relational semantics. The rows of the table are called entities, and they support functions like insert, update, merge, upsert, replace, delete, and query. Every entity, or row as you can think of it, in the table service can have up to 255 properties. The total data in an entity cannot exceed 1 megabyte. Each entity must have a partition key and a row key, and it also has a timestamp. The combination of the partition key and the row key forms a primary key that identifies each entity uniquely within the table. Tables are partitioned behind the scenes by Azure to support load balancing across multiple storage nodes. All the other properties in the entity are simple key-value pairs. The type of the value is just one of the standard .NET types: string, binary, boolean, datetime, and the like. But again, just to reiterate, there is no fixed schema built into the table service itself. A developer may choose to enforce a schema on the client side. Here, we see that a table can have a ragged shape, with one row having a field that other rows do not. There's no strong typing. Values in a column may have different varying types. Querying the table service is per the ADO.NET Data Services specification. In general, you should endeavor to always include the partition key to limit the scope of your query to partitions always served by a single storage node. Previously, I mentioned that the partition key allows Azure to scale queries to the table service across multiple storage nodes. But it serves other purposes too. Since entities with the same partition key are stored together, the cache performance of doing table scans will be much better within a single partition. Also, if you wish to group multiple write operations into a single atomic transaction, then they must exist within the same table partition. Naturally, it follows that you should not use distinct partition keys for every single entity. This slide illustrates an automatic feature of Azure Table Storage. Range partitions will group entities that have sequentially unique partition key values to improve the performance of range queries. This prevents a range query from needing to cross partition boundaries or server boundaries, which can negatively impact performance. The Azure Table Service uses partitions to automatically load balance reads and writes to your data. When there's a lot more load, Azure will move partitions to additional servers and fan out your data. As load decreases, Azure will condense the data back down into a fewer number of servers. You do not pay any extra for usage of these servers. It is automatic, and the scalable load balancing is built into the pricing of Azure Storage itself.
In this video, I'll use the IPython notebook because this makes it easier for me to show blocks of code and what's going on. If you want to follow along, you can place these code snippets into a plain Python script. You don't have to use the IPython notebook in order to use the Azure Python SDK. To start the notebook, I just type IPython notebook. I'll create a new notebook, and we'll get started with some imports. These are several libraries we'll need, including the CSV module, and of course the Azure.Storage Azure SDK module. Now what I've done is placed my account name and my key directly into a module in this directory called Azure Secret. This is to avoid having to type them explicitly as strings here and then needing to blur them out for the rest of the video. I'll also define our container. And with this information, we should be ready to create a handle to the Blobs service. Now we can write a little code that lists all of the blobs inside that particular container. Now we can programmatically write a new file, create a temporary file here in our current directory, and we can upload it to Azure. By going back to Azure Storage Explorer and hitting refresh, we can see that indeed sample 2 was uploaded, and we can view its contents. We can also delete it. And once again, we'll check in Azure Storage Explorer that indeed it has been deleted. Now let's do something more interesting. We'll grab the contents of the CSV file stored in the blob, and we'll create a new table out of all of the rows in that CSV file. We can check that there's a lot of data there. We can even print out some of it. Great. Now we'll create a new table. And now we'll ask the table service to actually create the table. Now what we'll do is write some code which will first split the contents of the CSV file on new lines, and we'll just take the first 20 lines of that CSV file, and using the dict reader from the CSV module, we'll convert every single line into a dictionary of key value pairs. Then, using those keys and values, we will create a new Azure entity object, and then at the end here we'll tell the table service to insert that entity into our new table we just created. Finally, we'll print the row to see what our successful insertion looks like. Now we can see it going and inserting every row one at a time. And now when it's complete, we can go over to Azure Storage Explorer and click on the Tables button, hit Query, and we'll see all of our rows inserted.
In this video, we looked in more detail at the blob and table storage services of Azure. These provide a very flexible data model for many kinds of applications, and scalability and reliability is built into their design. As you design next-generation data processing and analysis codes, it's worth thinking about using Azure Storage from the start so that your code can naturally scale and is naturally fault-tolerant. For more technical information on these and many code examples, please visit MSDN and windowsazure.com. Thanks for watching.